Alright, g'day. So today I've created a pair of dual LPs, the top one being the primal LP and the bottom one being the dual LP of the primal. Now, what we're going to do today is I'm going to go through and solve the primal LP using the simplex algorithm, and I'm going to show you how we can find the optimal solution to the dual LP through the primal LP. Alright, so I've already created a simplex table and I've filled in the constraints and variables. Now, I've just done this because I tend to run out of time if I don't have it done already. So we'll just jump straight in, and we'll do that by looking at the reduced cost row. You'll notice that the most negative number is -8. Most negative number is -8. And from that, we're going to do the ratio test on the x1 variables. So the smallest one is, of course, S2. So we're going to switch that out to get x1. And from here, we're just going to start reducing the rows. Get 0, get 1, -11, 1, -3, and 6. So wait, why am I blanking for 3? Anyway, keep going. 1, 2. That should be 2, 0, 0. Oh, no, that should be -1, and that should be 4. Cool, so I'm just going through and reducing all of these rows. This isn't too complicated, and I know this isn't the root of this. And as you can see, we still have a negative number in our reduced cost row, so we're going to go through and do this again. We won't need to use x1 since we've already used it, so it's just between our first and third constraint. And doing the ratio test, we can see that 4/2 is definitely smaller than 3/1. So we will be reducing this row. That becomes 1, 1. Both of you become half, although you are negative. And this becomes 2. Cool. We'll add on to this row, make 0, 5. Not -half, just regular half. And half. Cool. Continuing on for the S1. Whoops, I forgot to change this to x2. So S1 is going to be 0. That'll be -12. That stays 1. -2.5. Oops, my 2 is a bit wonky there. And of course, -half again, leaving you with 1. Cool. We're going to keep going. 12 onto 29 is 41. 2, 6, and that's also a 6. And that's 40. Cool. So real easy. That's our simplex table completed and filled out. I know it's been done very quickly. Carrying on, from this we can observe that x1 is equal to 4 and x2 is equal to 2. We also know that s1 is equal to 1. Alright, cool. So we're just going to go on to doing the complementary slackness theorem. Since we know that S1 is equal to 1, therefore our Y1 must equal 0 because of our rule. So if we look back up here at our initial equation, we'll have to take our first two constraints, and Y1 is equal to 0, so we don't need the first variable in these two constraints. So we can just get Y2 plus Y3 is equal to 8, and -y2 plus y3 is equal to 4. And we know this because, again, going back to our rule, x1 is greater than 0. Therefore, our e1 and our e2, because x2 is also greater than 0, our e2 will both equal to 0, so there will be no excess in either of these constraints. And from here we can solve to get 2y3 is equal to 12, y3 is equal to 6. Substitute that back in to get y2 equals 2, and there we have our answer for the dual LP. Thank you for watching.